Let's restart from the previous video where we left with limits.h file, right? With the file that contains all the maximum values. That file contains a lot of defines, a lot of symbolic constants, which are pretty useful, which are handy in our video of today. So as usual, the workflow. Let's open the terminal command space. I type terminal, enter. Let's move into the desktop as always. And then very simply, let's open Vim with the program limits.c. Okay. As usual, let's include the file standard input output. With that, we can use the printf function. Then here, usually what I do with Vim, I press ESC and then O. You see how fast I can move between modes into Vim, pressing ESC from insert mode to normal mode. So I can use the shortcuts. In this case, I used O to go on the next line. O, a good mnemonic is like open me a new line. And what do? I include the file limits.h, the file that contains all my limits. ESC little o. Then I write my main function, which is int main, and then you know all the deal. Inside the main, there will be all my code. Okay, ESC colon write. This is my empty file. I just want to insert a semicolon inside my main function. The semicolon is when you want to leave the function empty, so you just insert a semicolon. This is a functional code, just doesn't do anything. Then what do? We go out this file. So I press upper ZZ. Okay? So I saved and I've exited the file. And I clear the screen, clear. I can also press Control L to make it fast. As you can see, Control L. And then what do? We do this command, gcc hyphen, namely this little line, h limits.c. Okay, enter. This command, I can see all the headers that have been included into my file. And I want to look for a specific one that you know from the previous lesson, which is this file here, the first one with the high 386. I copy. Then what do? I clean the screen, Control L, and then I cat the content of this file. Okay, enter. Cat stands for concatenate. So basically, show me the content of that file. I gave the command cat the path, namely the place in my computer where the file is. Inside this file, I have all these defines. Now we're gonna copy all of them like that. Copy, Control L to clean the screen. And then I go inside my limits.c. I remove my limits.h. And then I just passed all these defines. Of course, this is an artificial way of doing things. Nobody does that. Essentially, you include the limits.h file and you have all the stuff. Now, I did exactly this copy paste deal because I want to show you all these defines and I want to explain you these constants, okay? All right, so now we have our file with all these defines. So I make here a comment just with forward slashes. You just have to write these 2 slashes to insert a comment. A comment is a piece of code that is not read. It's for humans. It's just for us to write some comments, indeed, some details about a specific chunk of code. In this case, I'm going to write, these are all symbolic constants. Okay, so you know that when we use define, we are saying, hey, dear computer, dear compiler, when you see this symbol, namely these characters in uppercase, because this is a convention, when we have a constant, we usually use uppercases because it's very easy to see when we have a constant and when we have a variable. So it's a very good convention for everyone, for us that we are writing code, so we can at a glance understand where are the constants, and for other people. So back to us, these are all constants, namely when there is this series of characters in uppercase, we have a replacement with this value in our code. Let's write in my main a printf function and then a format string with the max value of an unsigned int is, and then a format specifier, in this case a u that stands for unsigned, and then just the char for new line. Don't worry if you don't understand by now what is this format string. I will explain this concept of strings much more in detail in chapter 5. This is a pointer essentially, so another data type, which is the nightmare of all the people because it's very difficult, even though I don't think. But anyway, you will see. By now, just think about that as a simple string that you can see in the terminal. And here you have a piece of data, namely a variable or a constant that you can insert. This U stands for unsigned values. And this is a simple chart that say, hey, when you finish to write this string, this line, just go on the next line. So here I have to insert my unsigned value, which comes from the unsigned int, which is this constant here, you see? Unsigned int max, which is this value. This is the hexadecimal notation. If you don't understand this notation, just watch a video that I've made about this idea of symbols and values. So basically, here I'm going to insert unsigned int max. Okay. All right. Let's save this file and exit. How do we do? Well, ZZ, upper Z, upper Z. Then we have to compile our code and then launch. So we compile, I can see there is a mistake, not defined. Okay, this is not code that is pertinent to me. In this case, you see, this is all knackish way to do stuff. So this is not code that should be inside here, essentially. I delete this file and I go back. All right, I compile and then I launch my code. So I do ./a.out, launch. As you can see, the max value of an unsigned int is 4 billion and something. You perfectly know this stuff. You know that this is a simple constant value. Let's understand better this idea. When we have this defined, we are indeed defining a constant, namely a value that will be inserted in my code before running. Let me explain better. Here we have a text substitution deal, namely, in our case, my program that starts basically here with my main function. And here I have one piece of data that is coming from a specific constant here defined at line 18, right? This one. The translation process is divided into phases. I hope you know this idea of compilation. Maybe you have seen the video that I suggested you. Basically, we have a preprocessing of the file, then we have the compilation of the file, then we have another part which is the linking phase, namely GCC is a compiler that is composed of many parts that are working together. It is a tool chain, essentially. So the compilation, the translation of my code from source code, the code I'm writing now, to binary code, the thing that my computer can understand, is divided into little chunks. This stuff, these defines, are managed from the preprocessor, which is the first step in my tool chain of compilation. Let me explain better. Let's go out this file. I do now gcc -p. This flag is telling the computer, hey, I want you to just pre-process this file. Okay, let's watch what is going to happen with the file. Enter. As you can see, I have all this gibberish. Basically, this is stuff coming from the standard input-output file. Inside here, we can find, for example, the printf prototype, the one we need in our program, essentially. The thing I want you to understand is this one. You see my main function, which is at the bottom of the file. Of course, all the other files indeed are at the top. So are included, are copy pasted at the top of my main function. Here in my main function, I have the symbolic constant unsigned int max that has been changed, right? With the value itself, which is in hexadecimal. As you can see in the pre-processing phase, we have a copy paste of the symbolic values. Let's write some other examples so it's going to be easier. So what I'm going to do in my main YY, this is the yank copy, the string, and then paste. All right. Then what do? I'm gonna change some words here. Int. So I have to change the format specifier here to D, that stands for digit. Here we change with long, LD, stand for long digit, format specifier. And here we can change with char max, for example. And here we insert a C, that stands for char. Now we change our symbolic constants. Here we have int max. Here we have long max, and here we have char max, right? Char max. Cool. Let's do the same process as before. So ZZ, clear, Control L, GCC -e limits. So we are going to stop to the preprocessing phase, enter. And as you can see in my main, I have the value substitution of all my symbolic constants. You see? I have hexadecimal representation, but also decimal representation. It is just a representation thing, but the value, the things that we are counting are the same. It's just the way it is represented. Of course, with the long data type, it's much better hexadecimal representation because you can crystallize much bigger values with less digits, with less symbols, of course. Anyway, I hope you understood the point. Okay, we have text substitution at the level of the preprocessing, namely the first step of the compilation. Now let's clear the screen, Control L. Let's go back to the file, vim limits. So this is a way of defining constants, namely to define some values that are not going to change. In this case, they are not going to change because these values are not stocked inside my memory when my program is running. This is just text substitution when I do define. Now I show you another way to declare some constants. So what we're going to do, we're going to just simply delete some of them. For example, now I shift to visual, I go to highlight all of these, and then I press D for delete. Okay, so now I have only these ones. I'm going to delete inside my main all the printf. So I do delete 3J. I also want you to learn Vim while I'm doing my stuff, so you can really improve in every way, right? You just can understand many things. And here this time, what I'm gonna do, I'm gonna press ASCII O, and then I'm gonna insert a constant. This time I'm gonna declare a constant. Let's do pi, for example. So constant float pi is equal to 3.14, right? Semicolon. All right, this is a constant declared with the constant keyword. Now let's do the same with the define. Define pi 3.14. Okay, so these are two constants that we can use in our programs, especially in my main. Now we have programs that are composed only by one function because they're only at the beginning, but you can understand the programs are very, very big. They're made up of many functions. So now I'm gonna write printf, double quotes, and inside the value of pi is %f, the stand for float, and the variable, namely the constant, is going to be pi. I wrote one constant in uppercase and the other one in lowercase just to show you the difference between the two, but constants generally are always written in uppercase. This is not a syntax error, but it is just very useful to have this standard for everyone. And what do? ASCII O, and then printf quotes the value of pi again is %f, new line, but this time I'm gonna use the lowercase. Okay, so now you understand very well this printf how it works. You have a string with the format specifier, which is a float, and then a new line. Every time I go in the new line, ZZ, save, exit, compile, GCC, limits, and launch, a.out. Okay, it works perfectly. Now let's understand this idea. GCC, and we're going to stop again to the preprocessor phase. Okay, enter. You see the difference here. This time, look at that. With my define, which was the first one, I have text substitution, right? I have this 3.14. So basically my GCC, every time as found in my file, in my program, the symbol pi, chars pi in uppercase, has made a text substitution, right? On the other case, you see here, I still have pi, which is the tag of my constant variable, right? Constant variable seem an oxymoron, but that's what it is. A variable is something which is stocked inside your memory and that can indeed vary. That's why it is called a variable. A constant, on the other hand, is still a variable, namely something which is stocked in your memory but cannot be changed. So it is a variable which is in a read-only piece of the memory. Okay, so don't make confusion with the nomenclature of the things, a constant and variable. They basically are, everything is a variable when it is inside my memory. It is a constant when it cannot change. So it's a variable that cannot change. So for this, we have this specific keyword. So here, this time, as you can see, I still have the name of this constant. I have not a text substitution. When my program is running, I have somewhere in my memory this pi. That's the main difference between defining a constant with the define preprocessor command or creating a constant with the keyword constant. Okay, now let's watch another program so you can understand better. Here, as you can see, I have a bigger program, so you can start to see bigger programs. I have, as always, my include standard input output that contains all the functions that I need, in this case printf, and then here I declare two constants. Okay, so I have two constants which are double, namely the real type with a bigger precision. Here the data type is going to be 8 bytes. The name of these constants, which is radius in centimeters, and then pi, which is the pi number. Here I have a big comment, as you can see, even from the color. When we have big comment, we have this notation here with the slash and the star, and then my main function. This time is a bigger than usual function. As you can see here, I have some calculations. What do I do here? Basically, you don't have to understand what is going on, but it is just a little program that is telling a lot about circles. Let's just run it and watch the output so you can understand better. Define by and launch it. You see, it is going to give you back a lot of information. A circle with radius 20 centimeters. What is the diameter, circumference, all the details. Okay. As you can see inside my program, what do I have? Here I create some new variables, which is the radius in meters, circumference, area, and circumference, and area again in centimeters. These are called expressions. Basically, this is what the program is doing, is taking all this data and is making all the calculations. Like in schools, these are expressions that are going to be solved. But at the end of the day, these are just numbers, right? You have pi, which is a number, namely pi, which is a constant saved here. Then you have radius, which is another number, which is here. So it is derived from this expression here, and so forth. Look at the program. You see radius, cm. You see how easy it is to spot the constants, given that they are written in uppercase. Look here, radius cm, radius cm, radius cm, pi, pi. Okay, that's why we always write in uppercase the constants. And usually constants are visible to all the functions. Now you don't understand this point because we have only one function. But when we write constant double that you see here outside the functions, these are gonna be visible from everybody. Essentially, if I did this, namely copying this constant here, this constant would have been visible only for the main function, not for all the other functions that now you don't see because there are not. But you will understand this idea while doing all the exercises. I can delete this. Now, why these constants are very handy, my programs. As you can see here, I can very fast change the value of the radius of my circle to 42, for example. ASCII, I compile and then just run. And as you can see, the program has changed every part with the new value, 42. Let's go back. Now, for example, I'm gonna do 100, ZZ, compile, launch. Same idea, right? You have created a program that's very easy to use from everyone, just changing the inputs. Almost trivial, right? So you put at the top the parameters that you want to change. In this case, I have radius and pi, which are going to be constant inside my program. Pi is by definition a constant, even in mathematics. And radius is a constant in my specific program. So in all my program, the radius is going to be 100. As you can see, I have the radius that is used in different parts, here, here, and here, and here. So in all my program, that is a constant value. I don't have every time to rewrite all the values in all these spots. Okay? That's why constants are very useful, because they allow you to change in many parts of your code a specific value. And as you can see from this program, it's the main idea. You understood that the difference between define and const is that the values which are after the define are not saved in memory in your program, while the constants are just stuff which is stocked inside your memory, just you cannot change. All right, this is a briefly overview about constants that I give you, which is not in the book, but now let's start from the paragraph 2.3. So it's starting with the concept of suffix. These suffixes are used with constants, namely, they're gonna specify very, very well to the compiler which data type is that specific value. Let me explain better with code. All right, very easily, I have my usual blueprint of the main function with the inclusion of standard input-output. Now I declare a float data type. I call it NBR, and I give the value 3.14, okay? All right, very simple. Here I've declared, hey, dear compiler, I want 4 bytes in memory. This is gonna be a real value, so arrange the bits accordingly, and the value of this variable is gonna be 3.14. Name is gonna be number. Do you see a problem here? Nope. I don't either. Nobody sees a problem. But there is a thing here. Let's understand it better. Now I'm gonna compile this code. GCC suffix.c. No problem. It's compiled. Of course, it doesn't do anything because there's nothing in this program. I just have a declaration of a variable. So let's go back and let's append here the f. See? Again, ASCII, compile, run, nothing, everything seems to work fine. So what is the use of this f? Now I'm gonna remove that f from there, ASCII, and this time I'm gonna compile with this specific flag, which is W conversion, and then the name of the file, of course. As you can see, this is a special flag that is gonna check if there have been in my code some conversion of type. Let's enter. you can see, I have a warning. What is a warning? A warning is when your code works, but maybe there is something that you didn't pay attention to and that maybe it's risky. Here, what is the warning? I have implicit conversion loses floating point precision, double to float. Okay, and it's telling me exactly where in this line. Of course, we have only one line, but I'll let you imagine when you have thousands of lines. Basically, it's telling me, hey, this 3.14 has been converted to a float. Okay, let's try to do something. I'm gonna do this. I'm gonna append an f, ASCII. I'm gonna do again the same GCC conversion, enter. This time, as you can see, I don't have any warning. Nothing has happened. What is this? What is that? Okay, every time you write a literal, for example, in this case, 3.14 is a literal value. What does it mean? Well, when you type a value for the first time, this is not yet anywhere in your memory, right? What is going to happen when you declare a variable? You have the compiler that is going to see this 3.14. And by standard, every time the compiler sees floating point value which has a point, without a suffix, like in this case, so it's going to see 3.14, going to say, oh, here I have a value. This is a literal value. And for me, the compiler, as the standard, as they have created me, I know that this is a double. Okay, so it's going to perceive this 3.14 as a double. For the compiler, this is double. That's what it's going to do. Okay, I need to stock this value inside this variable that is called mbr. So 4 bytes in memory, and these 4 bytes are called mbr. I have to take this value and stock inside there. What is happening? That I want to stock a double inside a float, right? And you know very well that a float is smaller than a double. A float is 4 bytes, while a double is 8 bytes. So that's why I have this warning. Is basically the compiler is telling me, hey, are you sure what you're going to do? What are you doing? Maybe there is some information loss here. Are you sure of what you're doing? That's what is going on. On a practical standpoint, nobody really writes the F at the end of its data type, or L, or all these suffixes that you see in this slide. Frankly speaking, that's too pedantic. Nobody really does. But you are here to understand, so now you know why. What is really happening now? For example, as you can see, if you compile without any flag, the compiler is not telling you anything, because this is normal. This is there is not critical loss of information. But keep in mind that this 3.14 in a long form is not totally equal to 3.14 in its float representation. Let me explain better. So I'm going to click O to open, and I say if 3.14 is equal to mbr, ask O, curly brace, enter, printf, okay, right? Normal. Ask O, curly brace, enter, else, enter, curly braces, printf. What do you print? What the fuck? Okay, semicolon. This is a very silly if then else control statement. I bet you know very well how it works, right? So ZZ, we compile it, suffix, and then we launch. What is going to happen? What the fuck? You see? Why? Why it doesn't work? Well, my friend, I told you, this 3.14 is a literal value, right, for your compiler. So it's going to say 3.14, a point, this is a real value. For me, it's a double. Okay, here what happened with this 3.14 is that has been converted to a float, right? Here we have a casting, as we say, namely we convert a value to another value. In this case, a bigger value to a smaller value can create a loss of precision. And this is indeed what is happening here. A loss of precision in the very small digits. For example, we can have a difference, I don't know, a float can be 111, for example, very stupidly, and here we can have 1111112, for example. This is the thing that is going to change from a double to a float, but nonetheless it is a difference that is making these two numbers different. Now I explain you in very shallow, simple terms to make you understand. But here, if I do that, look carefully now, this is the point. Literal value f. So I append this f to this value. Okay, ASCII, compile, and then run. Okay, normal. You see? So what I've said here, I've said to my compiler, hey, dear compiler, you see this 3.14? I know that you want to read that like a double, but this is not a double. This is a float. So it is a way to tell the compiler very pedantically, hey, this is this specific value, okay? It makes the code more readable, even for other people. And this is a way for you to don't fall into the trap of implicit conversion that, as you can see, can happen underneath the hood, because for the compiler, the code essentially is right. It happens a conversion that happens underneath the hood. As you can see, you can have bugs like that you cannot understand. And you see why this variable is not equal to that. This is going to be super tedious to find these bugs. Of course, don't pay a lot of attention to this stuff because frankly, I never see all these suffixes into the code. Just pay attention. This is a thing that you can do, and this is what it's for, okay? As you can see here, we can have a lot of suffixes, for example, LL, F, U for unsigned, and so forth. You got the point, right, my friend? Now, the book is telling us that we can have numbers, we can have values that have different symbols, right? You understand very well this concept. But to make it clear, let's write some code. Let's go in our terminal, and of course, I have my function boiler. I'm gonna do printf %d \n, comma, and here I have 42. This is a literal 42, okay? And for the compiler, when we have a literal digit, this is an integer. This is not a char, nor a short, nor a long, 4 bytes. Ask, I copy this line, YY, past, I go up. Then what do? I move one word at a time, and I change this 42 to 0x, so in hexadecimal notation, and I write 2a, okay? And here I write 052. Okay, ask, ZZ, compile, and launch. As you can see, I do everything in one command. This is compile my program, and this is an end, launch. Let's go. As you can see, I have 3 42s. Let's go back to the main. Okay, I forgot to insert the binary representation that we can do with 0b, and the binary of 42 is 101010. Okay, ask, ZZ, compile and launch. As you can see, my friend, it's everything the same deal. We are only changing the symbol, but the value is the same. I hope you understand this idea. I made an entire video about that. Any doubts, just check it out. So long story short, we can write numbers in this very cryptic, strange way. I have here 0x FUL. What does it mean? Well, the prefix is telling me, okay, I want to write an hexadecimal symbol. So this symbol is gonna encapsulate a specific value. What is this specific value? Well, this specific value is F. We all know that F stands for the value 15, right, in hexadecimal. Then I have my suffix, which is UL. That stands for unsigned long. So what is this number? This is an unsigned long 15, okay? That's all there is. Now you understand all the ways. For example, if you watch this number as a beginner, this seems like super cryptic, but it's silly. You just have to deconstruct step by step. And that's all there is, my friends, okay? Now we jump into a very important topic, which is the one of characters. You perfectly know by now that you can stock numbers inside your RAM. You can treat like a notepad. You can write these binary numbers thanks to your keyboard, which is the input of your system. And that's it. You have these 4 gigabytes, 8 gigabytes, namely 4 billions roughly, 8 billions roughly of bytes, these lines of 8 bits. You can write these numbers. In this case, I wrote 42, which is 4 bytes, written in 101010. You can see from the upper byte, right? 101010. Cool. How about characters? How do you write hello? Where are those characters? Well, for that, my friend, we have to introduce a very important concept, which is the one of encoding. We have the so-called ASCII code, which is the American Standard Code Information Interchange. Basically, what we did, what was the trick to send characters with these machines? Well, we can think, okay, we can stock numbers inside our machine in a binary form. We can make, very simply, make an association numbers chars, right? We can say, okay, the number 42 is, what is the number 42 is the star, okay? So every time I have in my memory the number 42, the binary 42, I know that electrical state can be deciphered as a star, as a chart, okay? So look here, I have my table, which is composed of 127 symbols. You immediately understand that this number is 2 to the 7, right? I have numbers here, I have symbols from 0 to 127, namely 2 to the 7, which is 128. I have 128 possibilities with 7 bits. A char is 1 byte. With 8 bits, I can very well encode all these chars. Now, as you can see, there is plenty of symbols. We start from 0 to 32, the ones which are at the top, which are basically for formatting reason. I want you to take a look for the value 10, which is the new line. The new line is the one we always use, which is the \n as the value 10. And for the 32 is the space, the char for the space. And all the other chars are just symbols. You can see the alphabetical chars, which are in upper and lowercase. Then we have other symbols that we can use for example, the plus sign, the star, which is the 42, the brackets, and so forth. Okay, so this is a clear mapping between numbers and symbols. This is very clever, right? Amazing. So let's understand better why, for example, the letter A, uppercase A, is the number 65. Why? So let's start from the binary representation of these values. We have 65. Look carefully here. I have 0, 1, 0, and then I have 4 zeros and a 1. 65. This is 65 in binary. Then I have 66 and 67. You can see from this binary configuration that it's almost trivial to see a 1 in this byte configuration, a 1, if we exclude, quote unquote, the prefix, which is the first 3 bits, okay? Same thing for the lowercase a. Look there, we have the prefix, which is 0, 1, 1, and then we have a 1, okay? Then we have a 2 and a 3. So if we discard the prefixes, quote unquote, the prefixes bit, what do we get? Well, we get this byte configuration, okay? Basically, we have a one-to-one mapping between the alphabet char and its respective value in the alphabet. You see, namely the letter A has the value 1, letter B, the value 2. The only thing that changes is the prefix. For example, for the uppercase ASCII letters, we have the prefix 010, and for the lowercase 011. That's all there is. Look how clever it is. So we can basically understand letters very easily from their binary configuration. Same idea, of course, for numbers. The value 0 is the number 48, right? 48 is 0011 and all zeros. 49 is the same thing with a 1, and so forth for all the other numbers. You see how clever it is? This is the number 1, number 2, and number 3. But this is not the number 1, essentially the value 1. This is the number 48, the value 48, that encodes the char 1, namely the symbol 1. The thing you're going to see on the terminal is a symbol that has the shape of a 1, which is encoded by the value 48, as you can see here, namely the value 49. 48 is the 0, okay? That's the idea. Don't inflate the value 1 with the symbol 1. The symbol 1, the char 1, is the value 49. The value 1 is the value 1 in its binary form. Cool. I'm sure you understood very well. So this is the overall idea of the ASCII code. You have this encoding, you have upper chars, lower chars, a lot of symbols, you have the integers. So you can stock electrical states in your RAM, right? This is the encoding for the alphabetical chars. This is very clever because I can very easily map upper chars, lower chars, and integer chars. Amazing. All of this just to telling you that this is not totally random. There is an idea behind this specific configuration. You may have already understood that there is a gap between the uppercase and the lowercase, which is of 32, the value 32. Why 32? Well, this is 2 to the 5. So we have these 5 bits that are going to contain the value itself for the char, right? But the chars in my alphabet are 26. So we have a little buffer that has been filled with some symbols. The cool part here is that you can very easily toggle between uppercase and lowercase, just adding 32 to a char. Why? Well, because there is a 32 gap between the two. It's very easy. You will see that to shift a string from uppercase to lowercase is very silly. You just need to add 32 to all the chars. Very simple. Now you understand also why we need only 1 byte for a char. And that's it. Now, I want you to emphasize the fact that chars are just numbers. As usual, let's create a main function with my boiler. Then what I'm going to do, I'm going to create a char C, which is equal to 65. Okay. So this is the upper A. But I can do also like that. Then I have int n is equal to 42. This is an integer. Then I do my printf over specifier d, new line, and then I do give me c plus n. I'm just adding a char with an integer. And what am I doing? Can I do that? Let's try. ZZ, compile and launch. Boom, I have 107. You see? This is 65 plus 42, right? Yes. All right. So you see that this char, the one written in single quotes, this is very important, single quotes, is just a number underneath the hood. It's just a silly number, a 1 byte integer. That's all there is. We just perceive this as a symbol, thanks to this mapping of the ASCII code. Here, if I write, hey, dear printf, you see this number c plus n, just take it as a chart, okay? Ask ZZ, compile and launch. K, 107 is the char K. Are we sure about that? You can do that. Man ASCII. So I search inside the manual ASCII value for k. What is that? Lowercase k, 107. Exactly. I quit. I press Q. Boom. So here, if I write 65 or if I write A, it's totally the same thing. Nothing really changes. Of course, if I write directly A, it's more human readable, right? It is a symbol for us, for humans, but that's the same thing. What happens inside the computer? If I'm also really stupid and I want to write in binary, I can do 0b. You recall the prefix for uppercase 010, and then I have 5 bits for the actual char. So it's going to be 000001 because this is the first of the alphabet. So here I do, please print me that char. Okay, see? ZZ, compile and launch. See? The letter A. That's all there is, my friend. The main, here it comes. I think you understand what is going on. Cool. So now I can introduce you to the concept of a string. I have my fabulous RAM in which I can write numbers. You understand that I can perceive those numbers as chars thanks to this mapping of the ASCII code. Now what can I do? I can basically write, essentially like if I add a pen inside my RAM, thanks to my keyboard, strings, phrases, texts. I can write books inside my computer in this fashion. Every byte is going to be a char, right? So as you can see here, I have a very silly string, which is hello. Just check for the binary configuration. This is the binary configuration of the numbers, and it matches the ASCII code representation. H is that specific number, E is that specific number, and so forth. At the end of each string, we have a so-called sentinel value, and the sentinel value is always the 0. It is the null char, as we call it, but it is a value 0. It's the integer value 0, the value 0 itself. That's all there is. These are strings inside our computer. That's the way we write stuff inside our computer. That's all there is. Now, in the book, there is written that we have to pay a lot of attention to the difference between a single quote x, a single quote char, and a double quote char. Indeed, there is a very, very big difference. They're not the same thing. The first double quote x is a pointer. A pointer is a data structure by which we will talk profoundly from chapter 5. And that's a string. You can see already now our string is made inside our computer. Basically, we have a pointer to a char, a pointer to a series of chars. A pointer is a data structure that contains an address of a specific variable, but by now you don't have to understand. You have to understand that when you see a single quote element, you're seeing a symbol that underneath it is just a number which maps the specific chars inside the ASCII code, and that's all there is. As you can see, when you see the single quote, you have a byte in memory with that specific binary value. And that's all there is, my friend, okay, about chars. Now, here they propose you an exercise which is string, namely, as I can see, to count the number of chars inside a string. To understand this exercise, you have to understand pointers. I already made this exercise, so I give you the link of my exercise. Well, this could be a good way to train your technical sophistication. Basically, find yourself your solutions. That's the superpower of programmers, and that's the skill that you have to develop much more than anything else, in my opinion, because developers have to solve stuff by themselves at the end of the day. So you can try to understand what is going on with this point. One last thing that I want to clarify is this one. We have a lot of chars in real world, like we have emojis, we have Russian chars, we have Arabic, we have Chinese. What do we do with those chars? What is the deal? How do we solve this problem? So now I want to show you how to write emojis and stuff like that in all the chars, which are part of the Unicode, we call. Unicode contains everything. So Unicode emoji. So to write an emoji into your terminal, you just need the code, the Unicode. For this is this one. So 1F601. I have printf Unicode F600, pad with zeros here, and then ZZ, compile and run. Let's recompile and launch. As you can see, I have my smile inside my terminal. Okay, what is happening here? Well, we have a very clever way to use when we need it, the ASCII code, and when we don't need it, the Unicode. Basically, this is the UTF-8 way of encoding chars. I highly suggest you to watch these 2 videos to understand this idea if you fancy. The first is this one, amazing, character symbols and the Unicode miracle. Very well done, interesting. And the second is this one, which explains very, very well how the stuff works. So you can very well understand what is going on with these chars. Basically, every time you're sending with your phone an emoji, you have this bunch of bits that are being shuffled around through the internet. All right, my friend. The book is introducing you also the numeration constant, which in my opinion is not super useful and super used. So I don't suggest you to learn. Just to know that you can do that, I suggest you this video, which is this one from Bro Code, amazing channel. NU, see NU, is gonna just lay you down the overall principles in a very easy, intelligible way. Just keep in mind that you can do this stuff. But the thing is that there's no point in learning a lot of theory if there is no actual practice, because you will forget. Remember that your brain is a forgetting machine. It's trying constantly to make some cleaning. It is garbage collecting stuff every day. So this is numb stuff I never used, but maybe you will. So this is a good video to watch. That's it, my friend. Enjoy. Thank you for watching.